Okay, so what we're going to do is we're now going to take a low resolution spec and make it a little bit more complicated by looking at the high resolution spectrum that will actually be observed for most past paper exercises. Now what we've got here is a simplistic C2H4Cl2 molecule which has a CH3 on one end, which is giving rise to the slightly larger peak on the right hand side, and a CH singular hydrogen, which is giving rise to the peak on the left. Okay, now we're going to look in more detail at the peak which is given rise due to the CH3, which is this peak on the right hand side. And as we've said, this peak originates because of each of the hydrogens generating a small magnetic field in the presence of an applied magnetic field by the machine. Okay, and that's what gives rise to NMR in the whole process. It's the rotation of the nucleus of a proton within a magnetic field. And that's what gives rise to the peak that you see in the low resolution spec. Okay. That magnetic field, though, is affected by not only the external magnetic field and the magnetic field that's generated by the protons you're actually looking at, they are affected slightly by the magnetic field of an adjacent proton. That's the key thing. It is on an adjacent proton. We don't look at anything further away than one carbon, but that adjacent proton is also generating its own magnetic field. It's not being looked at directly because that hydrogen there has its peak here. But the magnetic field of this proton is going to have an impact slightly on that peak, and it does so by affecting the shape of the molecule, by affecting the shape of the peak. So if we look at this molecule in a little bit more detail, and we just say that those CH3s are literally just a CH3 now, and we look at this specific proton, there are now actually two specific ways that this proton can exist. If you remember, what we were talking about before was the spin of the proton, like an electron, can align itself with the magnetic field, and all the examples we've done today have done that. We've aligned the magnetic field with the proton. But it is possible that that proton could go the other way. We only talk about vertical directions in this situation. But we could have the magnetic field being aligned with the proton, or probably vice versa, the proton not aligning itself with the magnetic field. Now, if we then scan a magnetic field and we try to pick up the low resolution peak of what we saw before, if you remember, we were looking at situations where we had B plus X would be the magnetic field, and then the machine, knowing what the size of the magnetic field was, could work out what X was. Then it's possible that the machine is now going to be measuring two different, slightly different magnetic fields when it looks at the peak of CH3. Remember, this is looking at the peak of the CH3. But what is going to happen is this CH3 peak is now going to be made more complicated by the presence of this adjacent proton. And actually, the CH3 peak now gets to observe one possible magnetic field peak. It now gets to observe a second possible magnetic field peak. And so what can now occur is, instead of seeing just one peak, as we saw here, what we actually now see are two peaks. One peak next door to another peak. We see what's called a doublet. Okay, so we see a doublet. And what we're going to do is, in the next clip, we'll just look at that doublet in a little bit more detail.